Hello student, today we are going to start a very important and new topic, that is the eigenvalues and eigenvectors. So how to find eigenvalues and eigenvector for any square matrix A? If A is a square matrix, then the characteristic polynomial of matrix A is determinant A minus lambda I. And if A is a square matrix, then the characteristic equation is what? Determinant of A minus lambda I equal to 0. For example, if we consider a matrix A is this order of this matrix A is n by n, means it is a square matrix of order n. Then determinant of A minus lambda I is a determinant. You can see here. So what is the change in this determinant A minus lambda I? Definitely here I means unit matrix or identity matrix of order n, and that is why I am getting change in this diagonal elements only. Means this diagonal element A11, it becomes now A11 minus lambda, because here in identity matrix only diagonally 1 1 1. So this is the characteristic polynomial of matrix A. If we consider that is equal to 0, then we will get here. So this is the characteristic equation. Here determinant of A minus lambda equal to 0 is known as the characteristic equation of matrix A. The roots of the characteristic equation of matrix A are known as eigenvalues of matrix A. It means that we have to solve this determinant and then find the roots of this characteristic equation. The roots are known as eigenvalues of that matrix A, and corresponding to each eigenvalue we can find eigenvector of matrix A. You also note that if A is a square matrix of order 2, then determinant of A minus lambda I equal to 0. So what is it? It is the characteristic equation of matrix A, and that is lambda square minus S1 lambda plus determinant of A equal to 0. So what is this S1? S1 is sum of the principal diagonal elements. If we consider a matrix of order 2, then the principal diagonal elements are here A11, A22. So addition of this, it is nothing but S1. And if A is a square matrix of order 3, then determinant of A minus lambda equal to 0 is lambda cube minus S1 lambda square plus S2 lambda minus determinant of A equal to 0, where S1 is the sum of the principal diagonal elements, that is the A11 plus A22 plus A33. If we consider a matrix of order 3, so I am getting this one. So what are the diagonal elements? A11, A22, A33. So this diagonal element addition. And S2 is the sum of minors of the principal diagonal element. Principal diagonal element means this A11. So what is the minor of this? Delete this row and this column. So I am getting here determinant A22, A23, A32, A33. Similarly, the others A11, A13, A31, A33, and the minor of last element, that is A33, determinant this row and this column. So what I am getting here? Here I am getting determinant A11, A12, A21, A22. So you find this S2 and you know how to find determinant of a matrix. Then by using this, it is easy to evaluate or easy to find characteristic equation. And after that you have to solve this characteristic equation and find the roots of this characteristic equation, and these roots are known as eigenvalues of matrix A. You also note that such type of things, because there may be the MCQs on these things. So spectrum of matrix is a set of eigenvalues. The trace of the square matrix is the sum of its diagonal element. So that is the trace of matrix A equal to A11, A22 plus A33. It means that here we consider a matrix of order 3, and that is why trace of matrix A equal to diagonal element summation. So A11 plus A22 plus A33. Next, the largest of the absolute value of the eigenvalues of A is called the spectral radius of A. If lambda is eigenvalue of matrix A, then the matrix A minus lambda I is singular. The degree of characteristic equation of matrix A is equal to order of that matrix A. Also, you note that the eigenvalues of diagonal matrix, upper triangular matrix and lower triangular matrix are the diagonal elements. For example, here diagonal matrix. So, what are the diagonal elements? 4, 2, 3. So, these are the eigenvalues. Upper triangular matrix, what are the diagonal elements? 1, 5, 6. So, these are the eigenvalues. And here lower triangular matrix, what are the diagonal elements? 4, 2, 3. So, these are the eigenvalues. So, you know that there may be MCQs on such type of matrices. So how to find eigenvalues and eigenvectors? So for that you must remember this table. So first the given matrix A, after that you consider the characteristic equation of that matrix A, that is the determinant of A minus lambda I equal to 0. And what are the eigenvalues? The roots of this characteristic equation are known as eigenvalues. So you find these eigenvalues. After that, to find the eigenvector, you consider eigenvector x equal to this matrix x, y, z. Here I am going to consider matrix A is of order 3. It is a square matrix. If we consider matrix A of order 2, then eigenvector x will be only x and y. Okay. So here I am going to consider given matrix A is of order 3. And solve this A minus lambda I matrix into x equal to 0 for lambda equal to whatever this eigenvalue. So lambda means here eigenvalue. So note that. So I will put first eigenvalue here. I will get here 3 equations, and by Cramer's rule I will solve these 3 equations and I will get corresponding eigenvector. Similarly second value, third value. But there are 2 possibilities. Which are these? The eigenvalues are non-repeated and eigenvalues are repeated. So if non-repeated eigenvalues, so one by one you put lambda equal to first eigenvalue in this equation and solve this by Cramer's rule. Find the corresponding eigenvector. Similarly for second and third. But if repeated eigenvalue, for example, there may be lambda 1 and lambda 2 equal to lambda 3. So in this case I will find first the eigenvector corresponding to lambda 1 because it is non-repeat. Directly we can find. But for the lambda 2 equal to lambda 3 means repeated eigenvalue. What to do here? So what here you have to find the rank of matrix A minus lambda I after substituting this lambda 2 or lambda 3. Is it? So here you put that value, repeated value. So I am getting one matrix. You find the rank of that matrix and suppose that rank is R. Then n minus r eigenvectors are possible. So what is n? N means number of unknowns. Number of unknowns means here x, y, z if order is 3. So n minus r. So sometimes maybe rank is 1 or 2. So I am getting n minus r supposed to be 3 minus 1 or 3 minus 2. So here 2 and here 1 means how many possibilities are there? There may be one vector and 2 vectors possible. So there are 2 possibilities, that is if 2 vectors possible and if only one vector possible. If only one, there is no problem, directly find it. But if 2 vectors are possible for repeated eigenvalues, then there we have to check whether the given matrix A is symmetric or unsymmetric. If suppose it is unsymmetric, then definitely suppose there are 2 vectors when it is possible. So see, n is 3. So what should be the rank? So I will get here the 2. So rank should be 1. If rank should be 1, it means that in the last matrix I am getting only one non-zero row and remaining rows containing all zeros. So how many equations possible here? For example here 1, 2, 3. So I am getting one equation. Is it clear? So here don't forget it is a x, y, z already there in this case, right? So here only one possible. So I am getting here only one equation, and by that equation I will put z equal to 0. Find the value of x and y. So I am getting one vector. So x, y, z corresponding values, and put y equal to 0. Find x, z. Again in the same equation put y equal to 0 and find corresponding x and z relation, whatever there. So these are two vectors possible if it is a unsymmetric. But if it is a symmetric, then we have to find, for example, here lambda 2 equal to lambda 3, and we will get only one equation here definitely, because rank is 1, then only two eigenvectors possible, and there I will find first eigenvector directly. It means that here by this equation I will find first eigenvector directly. So by any, for example, here I am getting the equation x plus 2y plus 3z equal to supposed to be 0. And here I want to find infinite many solution or any one vector there. So I can put here any value equal to 0. For example, z is 0. So what is this value? X equal to minus 2y, and I am getting the vector is nothing but z is 0 when we put y equal to 1, and this is. So you find first vector. So note that here now we have x1 and x2. How x1? Because if we consider lambda 1 and lambda 2 equal to lambda 3, so corresponding to lambda 1 we already have x1, and here by direct method I am getting x2. But there are three vectors possible, because for that repeated two vectors possible. Note that for that repeated eigenvalues there are two vectors possible, and that is why we want to find x3. In this case, when A equal to A transpose means symmetric matrix, you consider x3 equal to L(m)n, and then x1 into x3 transpose means this x1 and x3 transpose equal to 0, and x2 into x3 transpose equal to 0. So I will get two equations, and then by Cramer's rule you find the values of L(m)n, which is your third eigenvector. So without fail you remember this table, right? This diagram means this tree diagram. So by this tree diagram you can find eigenvalues and eigenvectors for any matrix A. So let's consider some examples on this eigenvalues and eigenvectors, means how to find eigenvalues and eigenvectors. So here is an example. Find eigenvalues and eigenvectors of the matrix A equal to 4, 2, minus 2, minus 5, 3, 2, minus 2, 4, 1. So how to find? So solution here. Step number 1. Given matrix A equal to, it is a 4, 2, minus 2, minus 5, 3, 2, minus 2, 4, 1. So what is the characteristic equation? As we know, so characteristic equation is determinant of A minus lambda I equal to 0. So therefore I am getting here determinant of 4 minus lambda, 2, minus 2, minus 5, 3 minus lambda, 2, minus 2, 4, and 1 minus lambda. Note that determinant of A minus lambda I, note that determinant of A minus lambda I, it means that it is a determinant with the same matrix, only this diagonal element changes to that element minus lambda. So it is a 3 by 3 matrix. As we know, direct formula, it is a lambda cube minus S1 lambda square plus S2 lambda minus determinant of A equal to 0. So you find S1, addition of diagonal element, it is a 4 plus 3 plus 1 of matrix A, it is 8. Check there. So S2 equal to minor of diagonal element. Here first diagonal element is 4, so delete this row and this column, and determinant is 3, 2, 4, 1. Similarly, find the minors of 3 and 1, means diagonal elements 3 and 1. So here 3, 2, 4, 1, first determinant, plus minor of diagonal, second diagonal element 3, it is a 4, minus 2, minus 2, and 1. Now minor of third element means 1, it is a determinant of 4, 2, and minus 5, 3. So find it. So that is equal to It is a 3 minus 8 minus 5, 4 minus 4, 0, and 12 plus 10, 22. So that is equal to, so solve it, and I am getting here minus 5, 0, and 22, and that is nothing but 17. And what about the determinant of A? Determinant of A, it is a 4 in bracket 3 minus 8, it is minus 5. Then minus 2 in bracket minus 5 plus 4 minus 1, and minus 2 in bracket it is a minus 20 plus 6, it's minus 14. So what is this value? It is a minus 20 plus 2 plus 28. It means that it is a 10. So I am getting characteristic equation is lambda cube minus s1 lambda square plus s2 lambda minus a determinant of A equal to 0. So this is the characteristic equation of that matrix A. Now find the roots of this. There are different methods to solve this polynomial equation. So one method is a synthetic division. You consider the coefficients. So 1, then minus 8, next is 17 and minus 10. And try for 1. What is the method? You try for 1. Here cross. So what is the addition of this one? Cross means here nothing. So addition is 1. So 1 into this 1. Here you write what is the addition of this 2. So I am getting minus 7. Then multiplication of 1 and minus 7 is here. So I am getting 10, and 10 into 1 here. If we get 0, then lambda equal to 1 is a root. But suppose if we get here non-zero number, so same thing you repeat for the minus 1, then 2, then minus 2, like that you continue. So once we get this lambda equal to 1, so by the remaining values I can find here lambda square minus 7 lambda plus a 10 equal to 0. So what are the roots? So you know how to find the roots or factors for this. Now solve this quadratic equation. We know how to factorize it. So lambda minus 5 and lambda minus 2 equal to 0. So I am getting here lambda equal to 5 and lambda equal to 2. So finally I am getting all lambdas, that is a 1, 2 and 5. So these are the roots of this polynomial, means these are the eigen values of matrix A. Now verify. You can verify here whether these values are correct or not. How? What is the addition of these eigenvalues? 1 plus 2 plus 5, it is 8, and that is nothing but the addition of diagonal element. So definitely the addition of diagonal element is 4 plus 3 plus 1 means 8. So yes. And now the determinant equal to product of that. So what is the product? 5 into 2 into 1, it is a 10. So determinant equal to 10, it means that these eigenvalues are verified. Now the eigenvector, step number 2, you consider eigenvector. Eigenvectors are step 2, eigenvector. So let x equal to, so what is the order? 3. So here 3 elements x, y, z. B, eigenvector. Now corresponding to each eigenvalue, we have to find one eigenvector. So consider matrix A minus lambda I into x equal to 0. So what is this A minus lambda I? Means given matrix. Here 4 minus lambda, 2 minus 2, minus 5, 3, 2, minus 2, 4, 1 minus lambda, and here also 3 minus lambda. Diagonal elements you check. And x is what now? Eigenvector. So x, y, z that we consider equal to 0. So for 1 by 1 value, so for first value of lambda means eigenvalue, So lambda equal to 1. See there, if we put lambda equal to 1 here, so I am getting here 3, then 2, and here 0. And then by multiplication of these two matrices, I am getting 3 equations. So right there, so I am getting here 3x plus 2y minus 2z equal to 0, minus 5x plus 2y plus 2z equal to 0, and minus 2x plus 4y plus 0z equal to 0. So by Cramer's rule, you find the values of x, y, z. What is the Cramer's rule? You consider any two equations. So I am going to consider these two equations. And here x upon determinant of coefficients of this y and z. So 2, 2 and 4, 0. Second is minus y. Now consider from the last two equation coefficient of x and z. So minus 5, 2, minus 2 and 0. And for z, coefficients of x and y. So minus 5, 2, minus 2 and 4. So actually this is equal to any constant k. So what I am getting? X upon here 0 minus 8 minus y upon 0 minus plus 4 and z upon minus 20 plus 4. So minus 16. So you can divide on this 8, 4 and 16 by 4. So I am getting x upon minus 2, y upon, instead of this minus 1 I am taking y upon minus 1 if we divide by 4, and z upon minus 16 by 4 means minus 4. So what is your x1 means first vector? It is a minus 2, minus 1, minus 4. But instead of this, I can consider here the least positive values are 2, 1, 4. Note that here one may consider minus 2, minus 1, minus 4. One may consider here the multiples, that is the minus 8, minus 4, minus 16. But normally you consider here maximum positive least integers. So that is why I am getting here x1 is what? 214 instead of this. So this is your answer. That is the x1 equal to 214. Similarly for lambda equal to second value. So lambda equal to 2. So what are the equations? So similarly for lambda equal to 2, what are the equations? Again I will put here in this matrix the lambda value 2. So I am getting three equations. So which are these? Now 2x plus 2y minus 2z equal to 0. Minus 5x plus y plus 2z equal to 0. And minus 2x plus 4y and 1 minus 2, that is a minus z equal to 0. Note that again by Cramer's rule. But suppose you will get here all zeros, means x0, y0, z0, all zeros. So that is not a correct eigenvector. And in this case, you just change the equation. Instead of last two, you consider first two. So 0, 0, 0 never possible. Means null vector is never an eigenvector corresponding to any eigenvalue. And that in that case, you consider first two. So what are these? So I am getting here 1, 2, 4 minus 1s. Again the same. Minus y upon minus 5, 2, minus 2, minus 1. And z upon minus 5, 1, minus 2 and 4. Note the case. So here you solve this one and find the values of x, y, z. So x equal to minus 1, minus 8, minus 9. Then minus y upon minus plus 5, plus 4, it is a 9, and z upon, it is a minus 20 plus 2, minus 18. So definitely you can find out now x2 directly to consider the least positive, maximum positive here. So all are negative. So divide by minus 9. So I am getting 1, 1, 2. That is your x2. For third value lambda equal to 5. So here I am getting minus x plus 2y minus 2z equal to 0. Minus 5x, 3 minus 5, it is a minus 2y plus 2z equal to 0, and minus 2x plus 4y, 1 minus, it is a minus 4z equal to 0. So by Cramer's rule again, x upon determinant minus 2, 2, 4, minus 4, minus y upon determinant minus 5, 2, minus 2, minus 4, and z upon determinant minus 5, minus 2, minus 2 and 4. So what are the values of x, y, z? You find here it is a 8 minus 8, 0, minus y upon, it is a plus 20 plus 4, 24, and z upon minus 20 minus 4, minus 24, and that is why x3 equal to 0, second negative, third negative. So divide by minus 24, I am getting 0, 1, 1, that is your x3. So what are these? These are the eigenvalues. Sometimes these eigenvalues we can write here lambda equal to corresponding value, that is 1. Here lambda equal to corresponding value 2, and lambda equal to corresponding value 5. So these are the eigenvectors. Why I am going to write like this? Because sequence doesn't matter. You can consider first value is 5, then 2, then 1, or 2, 1, 5, whatever there. And that is why one may write like this corresponding lambda. So these are the eigenvalues and eigenvectors. So I repeat it very simple way. That is, you can see now this method, that is a given matrix A, then write the characteristic equation determinant of A minus lambda equal to 0. Find the roots of this polynomial equation or characteristic equation, which are the eigenvalues of that matrix A corresponding to each eigenvalue. Now we have to find eigenvector. You consider that eigenvector x equal to xyz and solve this matrix A minus lambda into x equal to 0 for each lambda. There are two possibilities, that is the lambda means these eigenvalues are repeated and non-repeated. If non-repeated eigenvalues, find eigenvector directly. So in our case, these eigenvalues are non-repeated. So in the next video, we will see if eigenvalues are repeated and when symmetric, unsymmetric.